Today we look at Vivado HLS from Xilinx, and we're running that on Linux, and look at a little example from a C program, which is converted into mainly Verilog and some IP files, intellectual property packaging files, and then a compile combined with a bus model of the zinc board, which is a parallella board, and then we load the results of the silicon compiled C program on the parallella board and run a C program on that parallella board, also compiled on the ARM zinc processors on that board, to talk with the FPGA containing the silicon compiled C program to see if that whole path can actually work. It's a bit exciting because it's been a purpose since the 70s or so, to have the possibility to turn a C program into a chip, let's say. So I start up Vivado HLS. And we can have a look at the whole process of going from in this case, given C program that I adapted from one of the examples, to first an exported IP, intellectual property constellation, whatever you want to call it. So we have to check out which file this is. This is the right project. The project is just a directory. In this case, it's a disk share on another Linux machine over a Giga Ether connection, an FS disk share, where the project data and also the Xilinx tools like this Vivado HLS tool. Oh, that's just another picture. Vivado HLS tool is coming from. We look at the source. This is the source file. Essentially, it's a 64K short entries sine table that gets initialized by an FPGA program, which is necessary. You could also put the contents of that 64K word memory, which is composed of local, pretty fast memories in the FPGA. You could also have that prepared so that the image of the FPGA contains the initialization of that table, but here we compute it in the FPGA with a sine float point, float function. The actual function, this function, the lookup math, with two arguments, of which we use only one essentially, as I edited it anyway, is the main function, and here it gets the pragmas to tell it to use an XE Lite interface with these parameters, 3 parameters, return value and 2 in values. The directives are standard for this for this case. XE Lite, and what we do is the first run was first doing something else. It's not really. It's unimportant. It's just that it understands these C structures, and so it will return essentially after it's been initialized twice, which we don't really notice, except that it takes a little while, of course, initialization. And over the bus here, we will see that happen. I will press play first, so it now will start to compile this whole thing. Look at the windows. Essentially, it will return this tables entry as a short integer from minus 32,000 to plus 32,000 as two quadrants of the sine function from -1 to +1, which is +1 is 32,000 and -1 is minus 32,000, and the entry into the table is given by the invalue argument, inval argument. So we see the compiler running here. So 4.5 gig, 12-thread machine where this runs on, but both the tools and the design files come from another machine over GigaEther. And it does not really use multi-threading very well at the moment. But it works, at least it does for. Meanwhile, we can have a look at the board. No, it's already there. So here we have the results. Memory lookup table. We have 10 nanoseconds clock, which is fine for the Zinc 7010. Minimum latency 6 cycles. So if it just does a lookup, that it does the whole thing, probably including the interfacing, but I'm not sure, in 6 clock cycles. And the initialization takes about double the number of entries in the sine table, 130,000 cycles, which comes down to about half a millisecond, if I'm not mistaken. And we see here that sine has used 64 RAMs out of 120 and 35 DSP slices out of 80 and some logic. So it's all right, it fits, and it has created what we wanted. So we export this design. So we call it my ROM lookup. Okay. And okay. Exporting as Vivado IP, which means that the block editor in Vivado can recognize the schematic, let's say the netlist and some extra information and the bus information that this Vivado HLS tool has created from our single C program. The C program is pretty much, there's a .h file, and there are some settings to be included, like which processor you're using. It needs that sometimes, unfortunately. For the rest, there's not much data there. So mainly from the C file and the choice of interface, which are pragmas, it will create a Verilog model with the whole C functionality in it, which in this case, because of the sine function and so on, took about half the FPGA space. And now it's exporting that hardware model that it created from the C file, such that the Vivado can read that and connect it with the interfaces in the Zinc chip, which is going to take a little while too. So it has done what we asked, finished export. So we can then start Vivado. Vivado. What we do? I've already logged in the little board from the Parallel Kickstarter project, which has a Zinc 7010 from Xilinx, which is the chip we use. So we open the Vivado project for this example with a TCL command. Now we have updated we have changed the let's say the hardware block that is a C function, even though it's the same. But we must tell this package to upgrade the IP. So we do upgrade, and then here's the block editor that has succeeded. Here it is. We called it my ROM lookup. So here it is. It's got an AC light bus here, which is then connected to essentially the rest of the Zinc chip in a way that the Xilinx tools can recognize. These are blocks. This is the parallel, the GPIOs, the clock and resets, and some other interfaces. And this is a peripheral from Xilinx, which is built in the Zinc chip, sort of a connecting block, and we use an XZ light to connect here. You can do that automatically. So we can now say generate bit file, bit stream, and it will ask us to do the whole synthesis again. It remains the same as it already was, but let's do it again so that we can see the whole thing. Meanwhile, let's have a little look at the board. Here is the login. It's just on a local network. You can use X Windows. For instance. And I made this device available for a normal user. We're logged in as a normal user. This is the date of today. Meanwhile, we can see the system is working. This is the programmer's device for the FPGA. So this is where we're going to put the bit file that we're now creating into to load the FPGA with the C program that we intended and with the bus that connects it up with the processors of the Zinc. This is user I/O space that is necessary to write to the virtual memory that is associated with the bus interface, and this is where the result will be written of what we're doing now, turning the C program into a bit file. The bit file will be on that network partition from this machine. We can have a look at the little board. It's right here. Green light indicates it works. The red light here is because there's a debounce on the supply, and the big heat sink is that I don't need a fan. This LED here we can switch on. So it's just like this. Now the little LED here is actually on. Just it was off. That's user input output connected to the user I/O pins of the board with an adapter board. Just a test. Well, that works too. It would be a little work to change the connections to the C program, but in principle the C program can probably very fast write user I/O, for instance at 100 MHz or so as well. I didn't test that because then I need to change all those definition files. It's a strange. And this block diagram is understandable, but the hierarchy here, which we see here, is not exactly easy to follow. It's got a lot of wrappers, let's say, and which essentially is just saying to Verilog to put certain interfaces connected with other interfaces at a few levels of hierarchy. It's not overly complicated, but it's a lot of work if you're not handy with it. It's not running right bitstream. Okay, I'll look at the design. So here we see the usage of the LUTs and so on, and all the built-in chip. So this is the chip being used. Outputs. These are the CPUs. About half full. We don't need this. So if we now look at the parallel board, then I look in the history here. Here, this file, everything is right. Let's check it out. Yeah, all right. We have a little break because I had to change the video. So this is the latest file, and we can put this file therefore in the device. We just use this device of the zinc chip and put our latest design file in there. Okay, that goes very quick. And we need the test C program, which I'll show you. That's this test program here. And essentially, this is stuff about timing things. Then here we have sort of, you know, some text about measuring timing, which is not essential to the example now. I use this from an example I had at a forum for this board. So this opens up a virtual memory and for the input-output, and there is a specific module necessary to load into the operating system kernel of the ARM processors to make it recognize this bus interface and the memory associated with it. Here I set the values up for the return value, the in value, and this unused IDX data parameter. That's just offsets that come from a specific interface C file that Vivado HLS creates. So there are these addresses the offsets can be found, and the base address we get back from the opening of the virtual memory that we just did. Then there's just a loop where apart from a lot of timing and a couple of debug statements, we put in the two arguments and we let the hardware know that we want to execute the function based on the arguments we put in the device memory locations. And yeah, if we compile this and run this, then we can enter a value or two values of which one is ignored. That is the sine value. The first time we get a long delay, relatively speaking, half a millisecond or so to fill the lookup table. After that, it has filled the table already, and we'll skip that part, and we'll just do a lookup, a short lookup in a 64 kilo long sine table, half sine wave table from minus pi and a half to plus pi and a half divided by half. And yeah, so I didn't make the same function here in the C file because I just tested out with some values I knew. So if we compile this, we get then the return value and some timing and also some interface handshake data that I was interested in. Not essential for the demo, but you know. I think the C compiler command is still in the history. Okay. Here's our new to run some summertime application. So we have loaded the FPGA, so I can start the application. Just fill in 2 zeros for the input arguments to the C program, and it starts to run. And then it tells us back something about signals. So here it goes from 4. Just after we said go, it goes to 1, and then it goes to 6, and then it remains at 4. Those are control bits in the interface memory. And it says here that the main time here, 0.6 milliseconds, was being spent, and that we had our loop. I had a little loop to wait for those intervals, for those interface signals to change. Almost 4,000 loops it took to fill that half millisecond. So that figures, and then we have the answer, the readout, return value, minus 32,767, probably correct. So now there is no delta t. This is accurate, hopefully anyway, and there is no looping over the handshake protocol because it's immediately cleared the busy signal, so to speak. So we fill in another. This should be about halfway the table, or exactly halfway the table, depending on how you round it. So that should give us a return value of 0. Red value 0, and then we can take the full table. That should be almost the highest value. This doesn't matter what we fill in here. And again, no delay and no iterations over the interface acknowledgement signal. 32, that's the highest value, that's right. So this is plus pi divided by 2. And in a short table, 32,767 is the highest value, highest positive value. So our program works.